Hello, everyone. This talk is part of the workshop on local algorithms 2020, and my talk's title is Locality and the Stochastic Matching Problem. In this talk, we will see an arguably surprising application of distributed local algorithms in the analysis of a completely global algorithm for the stochastic matching problem, which is more of a combinatorial problem, not really in distributed or local settings. And what I talk about is based on joint works with Behnezhad and Mohammed Al. So let me start with problem definition. We are given an arbitrary graph G along with the parameter P, and each edge of this graph G is realized independently with probability P. So a realization of G is a random subgraph that includes each edge of G independently with probability P. What we can do, we are not aware of this realization, but what we can do is to non-adaptively query a subset of edges of G to see which are realized. And then the goal is to find a large realized matching by querying few edges per vertex. More formally, given this graph G and this parameter P, we have to pick a degree-bounded subgraph Q of G that achieves a large approximation factor, where the approximation factor is defined as the following ratio. It is the expected size of the maximum realized matching of this subgraph Q that we pick over the expected size of the maximum realized matching of the whole graph G. This problem has many applications, for instance, in kidney exchange, online labor markets, online dating, and matching sparsifiers. Let me start by an example. So suppose that this is our graph G, which includes a set of outer edges and an inner click. For P equals half, a typical realization of this graph looks something like this, and its maximum realized matching will include all the outer edges, and also it augments it using the realized edges of the click. Now, if this is the subgraph Q that we pick, which is what we would pick if we random sample, for instance, the edges of G, then a realization of Q would look something like this, and then the maximum realized matching of Q would achieve close to, say in this example, a 2/3 approximation. But instead, if we also include all the edges, all the outer edges in our sample, then the approximation factor would be much better. Okay. So from this example, we get that there are some edges that are important for the subgraph that we pick. So it's better to include those edges. And then there are some edges that can be used interchangeably. Let me quickly overview some of the related work and what I'll talk about. The study of this problem started in 2015, where Braum et al. Showed that a half approximation for this problem can be achieved by picking a subgraph Q, whose maximum degree depends only on epsilon and P. With the same guarantee on the maximum degree of subgraph Q, the approximation factor improved over time. And what I'll talk about is our result, which appeared at Stock 2020 this year, in which we show that the problem actually admits a 1 minus epsilon approximation. So in other words, for any epsilon larger than 0 and any realization probability P, we show that any graph G has a sparse subgraph Q of maximum degree dependent only on epsilon and P, such that the expected maximum realized matching of Q is at least 1 minus epsilon times the expected size of the maximum realized matching of the whole graph G. In fact, this dependence of maximum degree of our subgraph Q on epsilon and P is necessary. So it could be shown that any 1 minus epsilon approximation has to have a dependency on epsilon and P in the degree of the subgraph Q that's picked. However, the actual dependence in our work is exponential, and a nice open problem in the area is whether a poly 1 over epsilon P subgraph also suffices to get a 1 minus epsilon approximation. Let's also see the algorithm that we analyzed for this work, for this problem. So the algorithm is a simple Monte Carlo algorithm. We have a parameter R, which controls the maximum degree of subgraph Q that we eventually pick. And then we take R realizations G1 through GR of subgraph of this graph G. These G1 through GR subgraphs nodes are part of the randomization of the algorithm. And then from each of these realizations that we pick, we take a maximum matching, and our subgraph Q would be the union of these maximum matching. So pictorially, what happens is that if this is our subgraph, if this is our graph G, then we iteratively realize the edges of G and take maximum matchings. And at the end, our subgraph Q would look something like this. Let me also overview some of the techniques that we use in the analysis of this algorithm. So we start by partitioning the edges of G into two subsets, crucial and non-crucial edges. And this depends on the probability that each edge appears in the optimum solution, in the maximum realized matching of G. So in other words, if an edge has a relatively high probability of appearing in the maximum realized matching of G, we call it crucial, depending on some threshold. And then if it's smaller than this threshold, if this probability is smaller than this threshold, we call this edge non-crucial. So in this example, for instance, the red edges would be called crucial because they relatively, again, have a large probability of appearing in the maximum realized matching of G, whereas the blue edges would be called non-crucial. An important observation is that there are not so many crucial edges in the graph. All of them have a relatively large probability of appearing in the optimum solution. Therefore, the number of these edges is small. And in fact, if you repeat the Monte Carlo algorithm for enough iterations, then nearly all of these crucial edges would be part of our subgraph Q. So essentially, what we lose in our subgraph Q is a subset of non-crucial edges. And then the challenge in the analysis is to show that the realized crucial and non-crucial edges can augment each other and construct a large matching. And then the key idea that we use, and in fact, I believe perhaps the most important contribution of our paper, is to show that we can, in fact, use distributed local algorithms, and we call this algorithm a vertex independent matching algorithm. And we show that if we use this algorithm on the crucial edges, we can then augment the set of crucial edges part of the matching using non-crucial edges. So slightly more formally, what we do is we take this subgraph Q, and in the first step, we look only at the crucial edges, and we reveal only realization of crucial edges of Q. And then find a matching M sub C on the realized subset of crucial edges of Q using this vertex independent matching algorithm. And then commit the edges of MC to the final matching that we will record. And then we show that because of the various properties of this vertex independent matching algorithm, we can well augment this matching MC using the realized subset of non-crucial edges of Q. So in this figure, for instance, we first only look at the crucial edges. And suppose that these are the realized crucial edges, and we construct a matching and commit them to the output. Therefore, all the vertices, all the non-crucial vertices that have a neighbor part of this matching of the crucial edges would be ignored. And then in the second step, among the realized non-crucial edges that are left, we find a maximum matching and augment this matching. So let's see how this vertex independent matching algorithm is useful and what properties does it have. The first property is that for each vertex V, the probability that this algorithm matches V should be roughly the same as the probability that that this vertex V is matched in the optimum solution, in the maximum realized matching of G, via a crucial edge. Recall again that we run this vertex independent matching algorithm on crucial edges. So what we expect each vertex, it's natural to expect that each vertex should be matched proportionally to the same probability that it is matched in the optimum solution. But in addition to satisfying these marginal probabilities, there is a more important property that we expect this algorithm to satisfy, and it is the independence property. What we mean by that is that for most subsets of vertices, say V1 through Vk, we want the events of whether these vertices are matched or not to be independent. Of course, we cannot achieve perfect independence for all vertices, because if you're given that one vertex is matched, we know that at least one of its neighbors is matched. But what we prove is that for most subsets, roughly speaking, all of these vertices will be independent. So how is this independence useful? Again, it's useful in arguing that non-crucial edges could be used to augment the crucial edges. Right, so consider this example. E1 and E2 are crucial. Each of them should appear with probability 1/2. And then E3 is a non-crucial edge. Okay, suppose that there is some level of correlation in whether edges E1 and E2 are part of the matching or not. This correlation could, for instance, be in the following way. With probability 1/2, E1 is part of the matching, and with probability 1/2, E2 is part of the matching. The problem with this type of correlation is that E3 will, with probability 1, have a neighbor that is part of the matching. So we will never be able to use E3 to augment crucial edges. However, if the crucial edges are added to the matching in an independent way, there would be a probability 1/4 that none of E1 and E2 are part of the matching. And in that case, we would be able to use E3 and add it to the matching. Okay, now let's see how we can guarantee both of these properties and design this local algorithm and this vertex independent matching algorithm. And to design this algorithm, we use distributed local algorithms. And by that, I mean an algorithm that constructs a large matching on the whole graph. However, to only answer the query of whether a single vertex is part of the matching or not, we only have to look at the small local neighborhood of this vertex instead of at the whole graph. A byproduct of this type of algorithms is that if we are given two vertices that are far apart in the graph, then their solution, then their whether or not they're part of the matching or not would essentially be independent of each other. There are a few challenges to guarantee this, given the properties that we need to satisfy. One is that we are given these marginal probabilities. In other words, in addition to the graph, we are also given probabilities on the vertices, and then the probability of each vertex being part of the matching should be equal to this marginal probability. And this is further complicated because you're operating on a stochastic graph. Right? So when the algorithm starts to operate, each edge fails with probability 1 minus p. And then the final matching should be constructed only on the set of realized edges. And this also, note that affects the marginal probabilities. So guaranteeing both at the same time turns out to be a little challenging. And in addition, we want the algorithm to have a small round complexity. The round complexity, roughly speaking, is the radius around each vertex that we have to look to answer this query that whether this vertex is part of the matching or not. And it's important to achieve a small round complexity because we want a good level of independence between vertices. And a few fun facts about this local algorithm overall is that the round complexity of this local algorithm for our purpose of analyzing this algorithm for stochastic matching can in fact have any dependence on the maximum degree of the graph. But even a small log star n dependence on the number of nodes is undesirable for our setting. Unfortunately, for approximate maximum matching problem, if our goal is to only guarantee a large algorithm of large matching in expectation, we can get around this type of log star n dependencies in the round complexity. And again, this I mentioned at the start of the talk. We are using this local algorithm to analyze a completely global algorithm. Note that this algorithm that we are analyzing from each realization picks a maximum matching, which is of a global which is more of a global property of the graph. You cannot find a maximum matching locally. So to conclude, we show that the stochastic matching problem admits a 1 minus epsilon approximation by picking a subgraph whose maximum degree depends only on epsilon and p. Dependence on both epsilon and p is necessary to achieve a 1 minus epsilon approximation, but the nice open problem is whether a poly 1 over epsilon p degree subgraph can also achieve a 1 minus epsilon approximation, which we conjecture to be correct, but we just don't know how to analyze it. And another more open-ended question on a future direction is whether a variant of this vertex independent matching algorithm could be used to get improved approximations for various other settings of the matching problem, for which this 2/3 approximation appears to be a barrier. Thank you.